Why this empirical model? Why it is necessary? Now, it has a wide application in model-based control strategies, right? This empirical model. Now, what is a model-based control strategy? In model-based control strategy, we pursue the superior system performance. In which respect? In respect of two types of control that we have discussed. One is a set point tracking, where we have a variable reference that you have to track, or in case of a regulation problem. First one is a server problem, or in a regulation problem where the set point is more or less fixed, but there are chances of disturbances. So you have to design the control system so that it has a better or adequate load disturbance rejection. And this has widespread application in process industries. Okay. Now, this control-oriented model identification method that we'll be discussing today, that is a empirical modeling, it has become increasingly important and popular, especially in recent years, because it has some advantages, right? Now, prior to that, the process modeling in industrial or in chemical engineering have been generally based on the first principle equations, that is, conservation of mass, energy, or the equilibrium relationship from thermodynamics, or the chemical kinetics, or equipment geometry, and so on, which relates to the basic fundamental principles of physics. Now, in contrast to that approach, there is a fundamental model in control oriented process identification, where your objective is to design a control system for the given process. Our objective is to obtain a transfer function model. That is very important. We intend to obtain a transfer function model. The purpose of the transfer function model will be that it should reflect the dynamic response relationship between the manipulated variable and the control variable. The manipulated variable is that variable which is changed or altered so that the controlled variable or the desired output variable, whatever is the output variable, will have the desired effect. So this relationship between this manipulated variable and the controlled variable, which is called the dynamic response relationship of a process. So our objective will be to develop a transfer function model that will reflect this dynamic response behavior and from the point of view of system operation. Okay, so our objective will be to obtain this transfer function based on this manipulated variable to controlled variable response. Okay, now for this objective, that is our objective will be to provide an online regulation principle or online regulation algorithm for a process. So in this process, the process identification is very important. And how this identification should be carried out? The identification should be carried out at and around at operating point and suitable operating points or set point. It should be carried out, the identification should be carried out around a suitable operating point. Okay, so that this pointing, localizing this operation around a operating point is very important so that you obtain a transfer function model, a linear transfer function model, right? So that you can apply different tools of control systems to design the adequate control of the control loop, right? Now, this in control system design, the industrial chemical processes are generally classified into three categories. Go to the next page. What are the categories? First one is a Next one, stable system, an integrating system, and last, and obviously, an unstable system. So these are the three categories that is of systems that you face in industry or in chemical process. And this categorization is done based on their output response to a step change in process operation. We just change any process operation or any process parameter in a step fashion and see or observe how the output response is changing. Based on that, we classify any process system into these three categories. First of all, what is a stable system? In stable system, the response following a step change will move into a new steady state. A new steady state is achieved. In integrating process, the response or the step response increases or decreases monotonically. Either it increases or decreases. There is no settling down. It never settles down. Decreasing, the rate decreases. It either increases monotonically or decreases monotonically. Contrary to the stable system, it never settles down to a steady state value. So this is an integrating system. Similarly, the unstable system is one where the output response, it never attains a steady state. It may increase or decrease monotonically, or it may diverge from any steady state in an unbounded fashion. That is, it will tend to go beyond the limits of a system operation. So, unbounded response. You may similarly argue that this is also an unbounded response. Yes, this is also an unbounded response. But it is monotonically increasing and decreasing means it's a linear. It increases or decreases like this linearly. But in this case, it may change in this fashion as well. This is also unstable system, right? So these are the three types of systems that you will face in process industry, right? There are another important aspect that I should mention here that is called the inverse response. That is very interesting. Now, what is an inverse response? Suppose we have a system, this T, and this is a YT. Say this is a steady state value. So we expect the response, if it starts from 0, to move like this and reach steady state, or it may move like this and reach the steady state. It may reach the exact steady state or may have some steady state error. But the response is normally like this. But there are certain systems which starts moving in an opposite direction, like this. Then it's changing its direction and reaching the steady state value. This type of responses are called the inverse responses, right? It's a very typical type of responses. Now, how do you relate these responses to a transfer function model? Suppose for stable process or the stable system, all the poles will be in left up plane. Then only you will get a stable response like the green ones. Depending upon the location, the nature of the response will change. In integrating process, there will be at least one pole at origin of S plane. Then you get an integrating response like this. If there are more than one pole at origin, then this straight line may not be followed. It may become a parabolic one. But at least one. If one is there, it will be like a ramp signal. And for unstable system, there should be at least one pole in right up plane. There may be more than one, but at least one. But all poles in left half plane for the stable system, at least one pole at origin for integrating system, and at least one pole in right half plane for the unstable system. It's very trivial things. Then what about the inverse response? This inverse response means this set of transfer functions will have zeros or zero in right half plane, right half S plane. So then, because of this right half plane zero, you will have this inverse response like this. This is also called non-minimum phase systems, NMP. So these are the different types of. Obviously, this inverse response maybe should be. We should only consider this inverse response for stable systems, because for integrating and unstable systems, we cannot achieve a steady state. So it is beyond our capability to analyze those. First, we have to stabilize them, and we have to make sure that they settle down at a steady state value. Then only we can analyze them. So our concentration will be on this stable systems. Okay, and we will try to improve their performance. Okay, and try to model the stable systems. Next, let us get back to the question that we started with, that why this empirical model is important. We have so far classified the different types of models that are available. That may be fundamental model, that may be empirical model, but the question still remains, why empirical model is necessary. If you remember, I have mentioned this in a few lectures back, that for many processes, it is not worth the time and effort to develop a fundamental model. Right? Because first of all, the purpose may not be that much dependent on the accuracy of the model or the intricacy of the model. Second, the more complex fundamental model you develop, it not only takes time to develop the model, but it may also take more time to solve the model to obtain the response. So that is also another caveat of this fundamental modeling. And if your objective is to tune just a specific control loop, and since you are dealing with control loops or feedback, the model accuracy is of not that importance. So in situations where there are a lot of complications involved in defining the dynamic equations of a system, we rarely go for the fundamental model. Then what do we aim for? We aim for an empirical model based on some standard empirical model. So we'll go for empirical model in such cases. These empirical models will be beneficial because it develops a transfer function of the plant or the process by performing what is called a plant test. On the actual plant, you can carry out some test, and based on the test result or response, you can design a empirical model. Now, what is the most common form of plant test? That is a step change in the manipulated variable. That is nothing but the controller output, and then we observe the process output, how the process output is reacting to this step change in a manipulated variable, right? And from that response, we obtain or develop the best match between the model output and the observed plant output via some empirical equations. Okay, so what do we do? We have the plant responses based on this step change tests, and then from that data, we try to fit a transfer function so that the response of the transfer function, when simulated, will be as close to the actual plant responses as possible. So there are different ways of dealing with this, but there are certain points that you need to keep in mind before you start developing an empirical model. First of all, the first point is selection of proper input and output variables. Why this is important? Because in many of the systems, this choice of input and output is not trivial, because most of the cases the system we deal with have multiple inputs and multiple outputs. That is MIMO system. And in such cases, even if it is not MIMO, if you have a particular manipulated variable that may affect a number of output variables. On the contrary, a number of manipulated variables may be responsible for a particular change in a particular output variable. So what you have to do, you have to choose very judiciously that particular manipulated variable corresponding to an output variable you are concerned with, which will have the most significant effect when provided with a step change. So that selection is obviously not trivial, and depending upon your purpose, the selection will change, right? So for the time being, we shall consider that the selection of proper input and output variable is already done. We know the transfer function we need to derive between this input and this output. There is no controversy over there. That is already selected. The choice. Okay. Next, we have to provide the system with a step response. Right? Now, whenever you are applying a step response or changing the state of the system, say operating condition or any operating variable, before that, you need to make sure that the system is first brought to a consistent and desirable steady state operating point. Is very important. Consistent and desirable steady state operating point. You have to bring the system to a consistent. Consistent means the parameters are kept. If the parameters are kept same, and whatever changes happens, if the change is subsided, given the conditions, operating conditions, this steady state variable, steady state operating point will be repeated. You know, disturbance দাও, তারপর disturbance চলে গেল, ওই জন্য আবার এখানেই ফিরে আসে. It should be consistent. Given the situation, given the operating conditions, this steady state operation should be guaranteed at all instances. And desirable because when you are developing a transfer function model, you have to first choose an operating point around which you are actually obtaining the transfer function model. So you have to make sure that before making the step change, your system is at that desirable operating point. Right? And only then, once this is established, only then you change the input variable by a step. Number 3, very important, magnitude of this is very important. What should be the magnitude of the step change that you have to apply? Now, if the step change is too small, then what will happen? Then the measured output may not change considerably. Therefore, you may not have enough data to develop the model. And this is particularly very problematic for a system where the output measurement is itself very noisy. Because if the output variation is very small, you cannot distinguish between the noise and actual output signal. So what will be your objective? The objective will be to choose the magnitude of step such that it should be large enough so that the output signal to noise ratio is high, right? Sorry. The signal to noise ratio should be high so that you can clearly distinguish between output data and the noise associated with the measurement. Then only you can rely on the model you develop based on the output data. The next question that you may ask, that if the input change is too large, okay, you have said that it should be large so that the signal to noise ratio is high. But what happens if it becomes too large? Then also the output variable may not be reliable, because if there is a too much change in output variable, then there's every possibility that the operation or the variable will move off specification, that is out of its specification, or it may move into a nonlinear region where the behavior of the system will be completely different than what you are aiming to model. So that's why there will always be a trade-off, sorry, between the choice. It should not be too large, the step change, or it should not be too small. So this trade-off between being too small and too large is the task of the control engineer who aims to obtain the mathematical model, not mathematical, the empirical model, right, of the system. Let us see some of the methods used. So what we have to aim is to fit first and second order model to the step test data that we achieved. So the main advantage of this method is that a simple transfer function can be obtained, and that too graphically from a step response data. Now, the plot of the output response of a process with respect to a step change in the input is referred to as process reaction curve. This definition is very important. This process reaction curve. Okay. So our model building will be based on this process reaction curve. For the process of interest, it can be approximated by a first order or second order more linear model. Then from the process reaction curve itself, you can obtain the parameters of that particular model. For the first order model, we know what will be the parameters. K tau s plus 1, k by tau s plus 1 is the transfer function. And with respect to a step change of magnitude m, the output response will be something like this. So once you obtain the output response, we have to find out what are the parameters k and tau. These are two parameters that you have to calculate. M is known, so k and tau are the two parameters. So that will define the process model. Right? We'll see how this can be done. You know, for a given first order response, if you remember, the slope at t equal to 0 is given by 1 by tau. And finally, from this slope, you can calculate tau or the time constant. And finally, the gain can be calculated from the steady state change in u and y. There is delta u and delta y are the change. Delta is a change in input and delta y is a change in corresponding output. Sorry. So you already know the delta u, there is a change in input is m. So what you have to calculate, you just have to measure the change in output corresponding to this change in input m. And from this ratio, you obtain the gain k. So see, from the curve or the response, if you can find out the slope and the steady state value or the change in steady state value, then you can easily calculate the two variables of interest, the parameters of interest, tau and k. So this is the situation. This is a step response of a first order system. And see, I have drawn, it is tangent is drawn at t equal to 0 with respect to yt. This, when it intersects the steady state value of 1, the time it takes is nothing but the time constant, tau. So the intercept of the tangent at t equal to 0 with a horizontal line, y by k equal to 1, that means the per unit steady state value, occurs at t equal to tau. An alternate approach, you all know from this expression, If you put t equal to tau, it will be km 6.632, that is 63.2% of the steady state value. So from that also you can calculate your tau, that is the value at the value of time at which the response is 63.2% of its steady state value. That will also give you the time constant. It's very trivial, you know all these things. This is how we can obtain a transfer function or fit a transfer function to a process reaction curve if it is of a fast order nature like this. See, I have given an example over here where there is a continuous stat tank reactor and the feed flow rate is increased from 120 to 125. And the corresponding increase in temperature is given by this. So the temperature changes from 140 to 160, and the 63.2% will be 152.6. We'll see what we have done. We have drawn a tangent to this point, so it reached the 160 point at 5 minutes. So the time constant will be 5 minutes. Is it consistent? Let us see. If we apply the formula, K will be delta T by delta W. What is delta W? 5 and delta T is 20. So we get this K gain. And graphically, obtain tau equal to 5. If you consider the 63.2% method, then again you obtain this 152.6, and that is what you have obtained at 5 minutes. So transfer function model for that particular system will be given by K by tau s plus 1, 4 by 5s plus 1. So this is a very simple way of deriving the model. You do not have to fit any equation, any curve to the response. Just find out the transfer function that matches the response as close as possible. So a very few experimental steps will exhibit the exact first order behavior. But there's a problem. It can cover only a few systems because the true process model is neither first order nor linear. This is very important. So what do you expect from this step response? You'll never get that simple curve that you obtained because the actual system is neither first order nor it is a linear one. So only the simplest process that exhibit such ideal dynamics. It's obviously an ideal situation. So that the output data, another point, the output data is never that smooth. It is usually corrupted with noise. So the measurement always contains a random component. This noise will make it very difficult to draw tangents, right? If the value is very noisy, then on which values will you draw the tangent? It's very difficult to draw the accurate tangent. So the empirical model will not be that much reliable if the noise is too much. So another thing is that there may be a disturbance of unknown manner, of unknown magnitude that may also affect the result in the step test. Do not have any control over the disturbances. So this situation is also uncovered. That's why this simple model, first order model, is very difficult. So it can be difficult to generate a perfect step input. That's another point. We are saying that we will change the process manipulated variable in a step. That means it should change instantaneously. For physical plants, where there are physical components such as pumps and control valves, it will be very difficult to move from one setting to another instantaneously. So it will never be a pure step. Cannot expect a step like this. It will be like a trapezoidal signal. It cannot change instantaneously. Rather, it will change with a slope. So this finite time, it will give rise to a ramped response. So the very objective of step signal will be violated. So these are some restrictions that you normally face, and that's why we cannot completely rely on this empirical models. That is already discussed. We discussed that this empirical model has certain restrictions. So the main restriction is that the first point, that it is the plant is neither fast order nor linear. So and it's the output response will be very much noisy. The data will be very much noisy. Okay, and you cannot neglect the effect of the disturbances. And further, the developmental step is not that easy. There are ways of developing steps so that you can approximate step, but actually obtaining a step is a bit difficult using these physical components. So what we can do in order to account for this higher order dynamics, first of all, no system is fast order and linear. So instead of a simple fast order model, a time delayed term is introduced. Now, this it's been seen that this modification of introducing a time delay term can improve the agreement between the model and the experimental response to a great extent. So this is called the fitting of a first order plus time delay model. Okay, instead of simply k by tau s plus 1, we'll introduce a time delay. An actual scenario, the step response of actual plant is normally like this, the S-shaped curve. If you draw tangential to the point of inflection, you'll find that there's an amount of time theta within which you can assume the response to be almost unresponsive. After that, the response is getting a significant change. So this can be termed as a dead time or time delay portion of the model. And from that time delay portion, you calculate the time constant. So this is a typical response of a actual plant, which is neither fast order nor linear, which can be approximated by a portion theta and this straight line which is slope at the inflection point. And this theta determines or indicates the dead time or the time delay of the process model. So this is the actual thing. Okay, there is one mistake. This s should be k e to the power minus theta s plus 1. Okay, this should be up there. So this is a model that we're talking about. Instead of k, this e to the minus theta s has come. So what are the characteristics? The response will attain the 63.2% of the final response, not in tau time, but in tau plus theta. Because during this theta period, it is unresponsive. Only after the theta, it starts following this tau s plus 1 response. So theta n is a dead time, a time delay. Now, I already see the line drawn tangent to the response at maximum slope intersects this y k equal to 1, y by k equal to 1 line at t equal to tau plus theta. That is, it will indicate the time constant starting from t equal to theta, not t equal to 0, where the step change has occurred. The step response is essentially complete at t equal to 5 tau. This is the empirical formula of the settling time. So this is how the response will look like. So drawn a tangent and inflection point. This intersection will indicate the dead time, and this portion indicates the time constant portion. And it is assumed that during this period, the response is almost insignificant, and from that, it obtains a response like this. So it's like a fast order system, see, but with a dead time or the time delay. That's why it's called a first order plus time delay model. The rest of the response can be approximated by a fast order response. So what are the parameters that you need to calculate? You need to calculate tau, theta, and k. Okay. So there are different methods of obtaining this. Let me move over to the drawing board. So our response is plus 1. US is the input, it is output. So what is the response for t less than theta? Yt will be 0, and for t greater than equal to theta, yt will be not kp, it should be k. delta is the change multiplied by 1 minus e to the power minus t minus theta by tau. So this is the response. Kp, k into delta u multiplied by this. I think okay. So this is the actual response of the system. That's why we have seen that the response is looking like this. Up to theta, it will be like 0. Then it will follow this exponential curve. And this is your date type theta. That's why it is 0. And following this time, it will be like given by this equation. The next part. This part. Right? So the three process parameters, what are those? K, how you can calculate K? It is found simply as the long-term change in the process output, that is delta Y, the steady state change in process output by the change in the process input. Very simple. Now, how to calculate the time delay or the date time? Is the amount of time after the input is applied. The input is applied. If you draw the input in the same curve, this is the input is applied at t equal to 0. So after the time theta, the input, the output has started to change. So this theta is called the date time or the time delay of the system. So what is remaining? How to calculate tau? There are different methods of calculating tau. One method is the 63.2% approach. What does that mean? If you consider this equation, that is yt is equal to k delta u 1 minus e to the power minus t minus theta by tau. So if you replace t by tau plus theta as tau plus theta, then what you will get? You will get y tau plus theta is equal to k delta u, and this will be 1 minus e to the power of minus 1. So it will be like 0.632 k delta u. So this will be 63.2% of the steady state value, of the ultimate change. Okay. So from this, the time it takes to reach that 63.2% of the ultimate value, total time will be tau plus theta. So this minus theta will be the time constant tau. And this is your, say, 0.632 k delta u. Or it is nothing but your delta y, the actual change. The delta y is nothing but, if this is the steady state value, this change from this is the delta y, right? And this is your delta u. So this is one method. Okay, the time taken to reach the 63.2%. If you have that time, that will be tau plus theta starting from t equal to 0, and subtract theta, you get the time constant directly. Another method, the maximum slope method. Now what is this? The maximum slope of the output response to a step change occurs at t equal to 0, sorry, t equal to theta. So we can write down that this slope is equal to k delta u by tau, right? Or delta y by tau. What we're doing actually, we're assuming that if the output was left alone to change at this slope, then it will reach the entire change of delta y in tau. time. This is the definition of time constant, right? So from that, if you calculate the slope, you know the delta y, then you can calculate the tau very easily. Let's take an example. I first drawn the curve. The blue one is the actual response, and the red one is a somewhat tangential that I've drawn. Now, what are the values we have? The values we have here is say this is 8, and this point is say 30, and the output changes from 10 here to 16. So what will be the slope? Slope will be 16 minus 10 by 30 minus 8. That's the time. So it will be like 0.273. Then time constant tau will be delta y by slope. That is, what is delta y? 6 by 0.273. That is equal to 22. So by simply from this you can calculate the value of tau. And what about k? K will be delta y by delta u. So 6, and I have not written the delta u. I draw here. I'm just drawing the input here. This is the input. The change in input like this. At t equal to 0 is a step change. And say this is 2 unit. So delta u is equal to 2. So it will be 3. And what about time delay? Theta. If it is changing as 0, so theta will be 8 minus 0. So what is the final model? 3 e to the power minus 8s by, sorry, 22s plus 1. So this will be a first order plus time delay model, which will be approximation of the response obtained like this blue one. So this is another method which is called the maximum slope method of calculating the tau parameter, because k and theta can be easily calculated. And there is last another method. Which is called the 2-point method. 2-point method means you obtain the time required for the response to reach 2 points. That is, your tau is defined as multiplied by time required for response to reach 63.2% minus time required for the system to reach 28.3% multiplied with this 1.5. This will give you tau. This is the empirical formula, right? And delay will be, sorry, the time delay will be minus tau. Tau I will calculate from here. So by this method, you can easily calculate the time constant. There are other methods as well. I'll just show you. I've mentioned these two methods. There's another empirical method that is called Sundaresan and Krishnaswamy method. Same method. Here the 2 points are taken as 35.3 and 85.3. And based on that, the time delay and the time constant is calculated based on this formula. This is another empirical formula that we find in literature, right? Instead of 63.2 and 28.3. There are two other values, 35.3 and 85.3. 50% change in between them. Okay. So let me just come back to the drawing board again. So, so far we've discussed that for a given process model, which is not always a simple first order model, we need to fit a first order plus time delay model, right? Now, this first order plus time delay model, we have seen how the parameters can be calculated, the key, theta, and tau for the first order plus time delay model, so that the response will approximate that of a response obtained from a practical plant. I'm obtaining these parameters based on the practical plant response itself. But there are certain limitations of this first order plus time delay model. What are the limitations? First of all, whenever you're using this unit step response method, you should wait for the response to reach this steady state. Once you obtain the data that it has reached the steady state and stayed there for a considerable amount of time, then only you can draw the slope and calculate these points 30 and 8. Now, if this is 8 second and 30 second, there is no issue. Fine. Even if it is 8 minute and 30 minute, no point. Fine. But if it is 8 hours and 30 hours, it becomes a bit difficult. If it is 8 days and 30 days, then shall you wait for 30 days to see whether it is reaching a steady state or not? Or what is the steady state value? So it is very much not practical to wait for that long to obtain the steady state value or to ascertain whether it reaches steady state or not. So in some situations, in practical situations, especially in chemical plants, we have some very slow reactions, which takes days to complete in biological system as well. So will you wait for those long period to get the data? No, it's very not very advisable. Okay, so this is one very critical limitation of this process, especially for the systems having large time constant. So how to eliminate, how to tackle these situations? If you find a system with large time constant, instead of this fast order plus time delay model, we'll go for a model that is called integrator plus date time model. So what is the difference? In this case, your YS will be defined as in the previous case it was like tau s plus 1 k e to the power minus theta s. Since tau is very large, we have to wait for a long period to obtain a steady state. In those situations, we will be using this model, integrator plus date time model. So what is the response? It's fine. Oh, sorry. And for t greater than equal to theta, the yt will be equal to right. Now this gain k can be obtained from the slope because k is equal to the slope, simple straight line divided by delta u, and then the time delay is identified from the time it takes to change the output from its zero value after the input change has occurred. Right? So how the response will look like? If we draw two axes, right? The input change which has occurred at this point, and the corresponding output change will be so. If you look carefully, this will be your theta, and the slope. What will be the slope? Gain multiplied by input change. This is your time axis. This is your y t, and this is your ut. Now, what you have to calculate? You have to only estimate this gain k, because the theta can be calculated by looking at the response itself. Let us see an example where this integrating model or the integrator model will be preferred over the first order plus time delay model. See, suppose we have a distillation column, is a common chemical process where following a step change, say at t equal to 0 itself, this is the input. I'm repeating it here. Red one is the input. Okay, there's a step change in the input, and the corresponding change in the output is something like this. Right? And if you look at the time scale, suppose the step change has occurred at 0, it has started to react, say after some period like this, and then say if it's cramped, it has reached here after say 5 hours. It reaches steady state after 5 hours. So shall we wait for 5 hours to obtain the model? Is it advisable? Let us put some values. Suppose your initial value of this response was 2.705, and there's a step change to a value 2.715, and the output response corresponding to that changes from 99 to 99.8. So from that, you obtain the transfer function, and this is, say there's a gap of, it's not up to scale, right? This gap is say 2-minute delay. So this will be the first order plus time delay transfer function. But to obtain this transfer function, we have to wait at least 5 hours. But instead of that, if you had gone for this integrated plus time delay model, then what could have done? Now say the time scale is zoomed so that if it is 0, this is now 2 minutes, and this is say certain up to 30 minutes. You could have stopped at 10 minutes. It can be 10 minutes, 10 minutes. Only 10 minutes you have taken. Data up to 10 minutes. Then from the slope itself, you can calculate the gain, and the time delay is 2 minutes. That's fine. That is over. So your G2, sorry, S, the integrator model will be e to the power minus 2s, sorry, by s. It is fine. What about the gain? Changes in this period, say it changes from, I don't know, 1 second, I'm getting a call. হ্যালো, বলো। তুমি কোন ব্যাচ কোন ইয়ার একটু বলো। ও আচ্ছা আচ্ছা, আমি তো ক্লাসে আছি, তুমি যে পরে ফোন করবে 8:30 নাগাদ। হুম, ঠিক আছে। হ্যাঁ, ঠিক আছে। হ্যাঁ। So from that data, what you obtain, the gain is 1. So instead of this first order plus time delay model that require at least 5 hours of waiting, only in 10 minutes you can calculate the slope and obtain this model, which is not obviously the accurate representation of the plant, but still quite a good approximation of the plant. Okay, so it will give you a short-term approximation of the step response behavior of a system with large time constant, which can be approximated by this simple integrating systems. So this is another way of representing or obtaining the empirical model. Instead of first order model, you employ a integrating model. Then their response may be different, but for the purpose of designing a loop or tuning a controller, this model will be sufficient because you do not have to put enough effort, right? Coming back to the presentation now, there may be situations that this first order model, even with time delay, may not be enough. So what you can do, you can simply go for a second order model if it matches the response of a second order system. There is no time delay. Fine, there is no time delay. The point of inflection is at t equal to 0 only. Then you can obtain this model parameter t1 by t2 from this several step response cases are there. Okay, two limiting cases, tau 2 by tau 1 equal to 0, where the system becomes first order, and tau 2 by tau 1 equal to 1, that is for critically damped case. And otherwise, for different tau 1 and tau 2, there are different dampings. Okay, the larger the two time constants, the larger the two time constant is called the dominant time constant. It will dominate the response. So from this nature of the response, there's a way of calculating graphically by assuming tau 1 to the dominant one, we can obtain a first order model. Then you can incorporate the effect of the tau 2. This is another way of representing. We'll not go in details with that. This is another way of representing the second order model. There's another Smith's method where the model is assumed like this. It's a second order model, as you can see, standard second order system, but with a time delay. So procedure is to find out the time required for the response to reach 20% and 60% of the steady state value. Then you find zeta from a figure. I'll show you the figure next. From that figure, you find T60 by tau and then calculate tau since T60 is already known. And what is the figure I'm talking about? This is the figure. See, you first calculate T60 by tau given this zeta based on the ratio T20 by T60. Okay. Once you have this, then you can calculate tau because T60 is already known from this side. Okay. So from T20 to T60, you calculate zeta. Okay, this is zeta curve. Once you get the zeta, keep it there. You obtain T60 by tau from this curve. Since T60 is known, you obtain your tau. This is a method. It's called Smith's method, where you fit a second order time delay system. Okay, a second order system with time delay to the model. As the integrator, I already discussed this. Neural network we got covered. There's another part called discrete time dynamic model because since we are moving into the digital application of digital controllers, this discrete time dynamic model is very important. I'll just briefly go through them because we know the dynamic equation in continuous time domain is differential equation, whereas in discrete time domain this becomes differential equations. Right now, you can easily convert the continuous time dynamic model by converting the differential equations into finite difference discrete time difference equation. Okay, this approximation is very easy. I think you all know this approximation. This is the approximation of dy dt as yk minus 1 by delta t. It should be always backward difference approximation because we assume all our systems to be causal. That is, it is dependent on past and present input, not on the future input. So to maintain this causality, you have to always use this backward difference approximation to deduce a difference equation from a differential equation. Okay. So if you put this differential equation form into the equation, you finally get the equation. There's nonlinear one. So I'll give you a linear one. This is a linear equation. So you have to obtain the difference equation for this. It's a first order differential equation of a first order model. The transfer function is of the form the transfer function. So use the backward difference. So this will be the representation in discrete domain. Tau yk minus 1 delta t plus yk minus 1 plus uk minus 1 into k. So rearranging, you get yk as a function of yk minus 1 and uk minus 1. Clearly, you have gain and the time constants embedded in a special form. So this is how you can obtain a difference equation by rearranging the difference approximation, backward difference approximation of the differential equation. This is also carried out to second order system. Very simple, the second order system. You obtain an equation like this. Then, what is the advantage of this empirical model? If you obtain this difference equation, see, then the knowledge of uk minus 2, uk minus 1, and yk minus 2, yk minus 1 will be enough to give you a prediction of the output at the present instant. So what you have to identify? You simply have to identify A1, A2, B1, B2. If you have this identification, then you can predict, you can model the response. Because see, output at any instant can be represented as a linear combination of different inputs and outputs at different instances. These are all past instances, right? So this is how you can obtain a second order difference equation model, right? To obtain a empirical model. Obviously, it's an empirical model. So I've just touched this discrete domain design because in most of the cases we normally now use digital controllers. So this will be very helpful in programming your digital controllers, this difference equations. A simple algorithm, a simple loop equation will be sufficient. Okay. So I guess I will stop here today. Any queries? I guess. Any query? Okay, then I'll stop here today.
Thank you, sir. Thank you, sir.